Okay, everybody, welcome back. We're continuing. This is going to be part B of Chapter 2, Section 2 in our honors physics textbook. We're dealing with kinematics, particularly speed and velocity, comparing distance or displacement versus time. And in this segment, this last little segment of Section 2.2, we're going to be looking at the graphing of motion. Now, if you recall, in the last problem of the last section, or the last part of the section that we did, we had a sprinter running down to the end of a track and then walking back. All right, well, if you've got distance being covered and then coming back, but you also have time elapsing as well. So if you draw all this stuff on the same axis, it kind of gets muddy. You've got this time, so it goes down and then stops and then comes back. You've got this sort of time graph superimposed on top of this coordinate graph right here, where you've got your positive displacement and your negative displacement right here. Does this mean that time is going backwards? No, it means time is going forwards, but you are moving backwards, and it's just kind of confusing if you have one axis. So plotting your position versus time on two different axes is very useful. Now remember, our x position, we're still talking about the horizontal axis. Or I should say the horizontal position. That is, like, say, walking across the surface of the earth. However, time is always going to be graphed on the horizontal axis because we always plot the dependent variable on the y, all right? So the dependent on the y-axis and the independent on the x-axis. Time is always independent. Think of it like this. Time always marches forward no matter what. Time doesn't depend on anything. But your position, that is where you are, might depend on what time it is. So if you're moving a certain speed, how much time elapses dictates what your position is right there. So even though we're going to be talking about the x, you might say the horizontal position, we're going to plot it on the y-axis because your position, your x position, even if it's x, depends on what time it is. Hopefully the next little next graph that we do, the next slide, we'll make that into some sense. All right. Now keep looking back to this one right here because we have at time equals 0, he's going to be at 1 meter. All right. At 1 second, he's going to be at 3 meters. At 2 seconds, he's going to be at 4 meters. Then at 3 seconds, he's going to be at 2, and at 4 seconds, he's going to be at negative 1 meters. Let's see if we can plot that on two different axes. All right. So we've got a y and we've got an x-axis. Now we call it the y-axis, but we're really going to plot position right here, and we're going to call that x, our x position. So where you are horizontally is going to be on the y-axis, and of course that's measured in meters. Okay? And like I said before, on the x-axis we've got time. Time is going to be measured in seconds. All right, so let's put some tick marks on here. You need to be able to graph in this class, and so we're going to make our marks. Let's go from so that's 1 second, 2 seconds, 3 seconds, 4 seconds, etc. And I'm going to go into the negatives right here. So negative 1 meters, 0 meters, 1 meter, 2, 3, and 4. I think that's all we should need. Okay. So if we plot x versus y, or sorry, x versus t, the x on the y-axis and t on the x-axis right here, or t on the horizontal, I should say, maybe that'll make it clearer for you. What do we get? Well, look back at the previous slide that we have. I'm not going to flip back, but you can. What do we have? At time equals 0 seconds, when time starts, the object, whatever it is at the position of 1 meter. All right? When time equals 1 second, the object is at position 3 meters from the origin. At 2 seconds, the object is at 4 meters from the origin right here. Keep looking at the previous slide. At the time equals 3 seconds, the object is at 2 meters. And at 4 seconds, the object is actually at negative 1 meter right here. So if we were to connect all these dots, and you don't want to connect them in a straight line, but connect them in a curved line, you should get something Oops, I messed up that little part, that last part right there. Something that looks like that without that messed up area right there. Okay? This is a position versus time graph. And this is telling us that the object is moving in the positive direction. It stops and then starts moving in the negative direction. So this slope right here, even though the slope is changing, this slope is a positive slope. It's a positive change in position over time, and this is a negative slope right here. And we're going to turn that into something that means something to us. All right, so kind of look back at this, and I may flip back and forth to this graph as well, but how do we interpret this right here? All right, well, on a position versus time graph, the average velocity of an object during a certain time is equal to the secant line connecting those 2 points. Oh, what does that mean? Well, let's say for a second, let's go back. That line is a line that connects 2 points of a graph directly. All right, so if we start, let's go with green. All right, if we start here, and if we end right here, if we draw a straight line down just like that, that would be the average velocity. The average velocity is actually negative. Because look, over the whole trip, he starts in a positive direction, at a positive position, and ends up at a negative position right here. So really, on average, he kind of goes sort of negative. On average, he has a velocity that is negative, even though he goes pretty far forward and then comes back very far negative. We could say, on average, the secant line indicates the secant line between the beginning point and the end point indicates the average velocity. But look at the in-between points right here. What if we have an upward slope? Well, like this. The whole first half of the trip is upwards. Now, it's getting kind of less of a slope right here, but this is all an upward slope. That indicates a positive velocity. Indicates a positive velocity because we have if we connect 2 points right here, we have a positive change in x over a change in time. All right, so that's a positive velocity if you've got an upward slope, a positive slope. But in the second that trip right there, we have a negative change in displacement over time. So that means we've got a negative velocity. And for the whole trip, there's more negative velocity than there is positive velocity. So for the whole thing, this right here, this secant line says that, all right, well, all the other things being equal, you may as well just step back 2 meters in those 4 seconds because in all, you've got a lot more negative velocity than you do positive velocity right here. Does that make sense? I hope it does. That downward slope, let's make that red. The downward slope indicates a negative direction during the time interval, which means you've got a negative velocity. So let's take this graph that we just drew, and this is a much prettier version of it, and let's make a little bit more sense out of it. Okay, so he starts in a positive position, starts moving positively, but then for some reason turns around and starts moving negatively, starts going in the negative direction, and even winds up at a negative position right there. Between any 2 points, let's say those 2 points are point A and point B. All right, here we'll circle B with red for stop and A with green for go. If all we care about is just points A and B, we could say on average, even though he goes way forward and then comes back, on average, you could just simply connect a line between point A and point B. We call that a secant line. And whatever that slope is your change in position. That's what that indicates right there. Your change in position over the change in time. In math, we would probably call that your rise over your run. Here's your rise, some change in position. Here's your run, that is the amount of time. And so that would give you your average velocity for that time interval. Now, the reason we have a positive velocity is because we stopped time right here. All we said for now is that we care about A and B. For the whole trip, he winds up being more negative right here. But between any 2 points, you draw a straight line, and the slope of that line is your average velocity. Let's look at another 2 points. What if A were right here, and B were down here? Okay, if all we care about is those 2 points, well, look, you can see it's kind of a negative slope right there. But if we draw an exactly straight line, we call that a secant line, we're going to have a negative velocity between A and b. Because even though we have a positive time interval, because time is never ever negative, time is always positive. With a positive time interval, we have a negative displacement. It's less than 0. So therefore, that means that our velocity for that time period is going to be negative, whereas previously it was positive. But let's just say, for example, that we have a constant velocity. Now, this graph right here wasn't constant, was it? You went forward and then stopped and then came backwards in the negative direction, and that wasn't very constant. But this graph right here is constant. Why? Because we have a constant slope. We define velocity equals a change in displacement over the change in time. All right? And all these displacements right here, this displacement over that time, and let's do a different color, this displacement over this time, those proportions, the changes in displacement over corresponding changes of time, are going to give us the exact same slope, which means it's the same velocity all along this line right here. All right, so a constant velocity, if you have, I should say, if you have a constant slope, that means that you have a constant velocity. A constant velocity results in a constant slope. Okay, so that's our section 2.2b, because this is a continuation of 2.2a. Hope that made sense to you. If you don't understand anything, make sure you come and see me or ask me. But in the meantime, thanks for watching, and I'll see you on the next one.